Hey students, today we are going to look at L'Hopital's rule. Today we will use L'Hopital's rule to evaluate limits of quotients. So we're headed back to limits, that very first topic that we discussed together. So L'Hopital's rule is used to evaluate limits of quotients, where we have the limit as x approaches a of f of x over g of x, where f of x over g of x as x approaches a has an indeterminate solution, such as, and we've got two options for this, 0 over 0 or infinity over infinity. Now, when we first encountered 0 over 0 in the first unit, unit 1, we had to go back and simplify the problem. We had to factor, we had to FOIL, we had to simplify trig, we had to use the conjugate pair. Excuse me. All of that worked to get us to the solution, but I have good news for you. We don't have to do all that this time. All right, so L'Hopital's rule. Assume that f of x and g of x are differentiable on an open interval containing a, and that f of a equals f of g, g of a, which equals 0. Assume that g prime of x does not equal 0, but it does exist. Basically, you can't divide by 0. That rule is still true. If that's the case, when you find the limit of that quotient, what you're allowed to do is, what are those? Those are primes. You can find the derivative of both the numerator and the denominator, and you have the result that way. It works out. You're like, what? How come you didn't tell us this before? The reason why we couldn't tell you before is because you didn't know what a derivative was. You can't learn about a derivative till you know what a limit is. So it's this cycle that goes back and forth, but let's check it out. So the limit as x approaches 1 of x cubed minus 1 over x minus 1. So the thing that you still need to do is check out that first value. So you're going to put 1 in for x. So 1 cubed minus 1 is 0, and 1 minus 1 is 0. So this does result in 0 over 0. Now, quick note about AP notation. I've been doing a lot of reading online. You can't call these equal because 0 over 0 is not a number. And if you're going to use the equal sign, you have to have a number. So that's not okay. You can kind of throw an arrow on there. That's a little bit better, but not an equal sign. So once you verify that you have 0 over 0, that it's indeterminate, what you can do is find the derivative of the numerator and the derivative of the denominator. So this becomes the limit as x approaches 1. The derivative of x cubed minus 1 is 3x squared. The derivative of x is 1. Now you put the 1 in for x, and this becomes 3 over 1. There's your solution. It works. Now, I just want to show you that this does work algebraically and what it would look like. This factors. I don't know if you remember any of these, but this is difference of cubes. So this would be x minus 1, and then this is x squared plus 2x. So I have to think about this, plus 1. That's right. All over x minus 1. Now, the x minus 1s, those quantities would cancel out, and I could put 1 in for the x's. So this is 1. I'm goofed on a sign somewhere. All right. I don't know if you can read that. I goofed on my difference of cubes formula this morning. It's too early. This is not a 2. It's really a 1. All right, there we go. So now if I put the 1 in place of the x, I've got 1 squared, which is 1, plus 1 plus 1, which is 3. So I do get the same result if you don't mess up the formula. But L'Hopital saves us a lot of time, obviously. And when you see a limit problem on the AP exam, it's most likely this is the definition, or you got to use L'Hopital in some way. So let's look at example B. I'm looking at the limit as x approaches pi over 2 of cosine of x. So remember that this is really the cosine of x quantity squared. That helps. Cosine of pi over 2, and I know we're feeling a little unsure about that unit circle. So pi over 2 is at the top. The coordinates are 0, 1. Cosine is the x coordinate. So this is really 0 squared. Sine of x minus 1. Sine of pi over 2 is 1 minus 1. So this is 0 over 0. So it is indeterminate, which is good news. So now we can use L'Hopital's rule. And this isn't official notation, but I usually just leave myself a little note that, hey, I use L'Hopital at this step. So now it becomes the limit as x approaches pi over 2. Cosine squared of x, you actually have a choice. You can do a product rule or a chain rule. I'm going to go with the chain rule. So this is 2 cosine of x to the first power. The derivative of cosine is negative sine. In the denominator, the derivative of sine is a positive cosine, and the derivative of 1 is 0. So that's good news. Now, in order for things to work, you'll have something cancel out. The cosines cancel out. So this is now the limit as x approaches pi over 2 of negative 2 sine of x. So if we look at pi over 2, this is really negative sine of pi over 2. We already said the sine value is 1. This is negative 2 times 1, which is negative 2. All right, good job. Looking at letter C, if we put 0 in place of the x, e to the 0 is 1 minus 1 minus 1. Nope, that's a 0. Good grief, I can't substitute this morning. And then in the bottom, cosine of 0 is 1 minus 1. This is also 0 over 0. So indeterminate, which means we can use L'Hopital. So as a reminder, the derivative of e to the x is e to the x. The derivative of x is 1. The derivative of cosine is negative sine. And the derivative of 1 is 0. So now you got to try your 0 again. So e to the 0 is 1 minus 1. Sine of 0 is 0. Well, I've got 0 over 0. So now what do I do? You can do L'Hopital again. So one more time. The limit of e to the x is e to the x. The derivative of 1 is 0. The derivative of negative sine is negative cosine. So in the numerator, e to the 0 is 1. In the denominator, cosine of 0 is 1. So this is negative 1. The answer is negative 1. Are there any limits as to how many times you can do L'Hopital's rule? Nope. But if you find yourself keep going and going, like after 5 or 6 iterations, stop and see if there's some kind of error somewhere. 2 or 3 is more typical. If it's taking more than that, there's something kind of special going on there. So example 2, use L'Hopital's rule to evaluate the limits of the form infinity over infinity. So we just chatted about infinity over infinity is also indeterminate. You want to check infinity, e to the infinity is really still just infinity. Don't use equal signs here because infinity over infinity is not a number. But this is indeterminate, so we are allowed to use L'Hopital. The derivative of x is 1. The derivative of e to the x is e to the x. So this becomes 1 over e to the infinity. Now, we discussed this back in limits, but we haven't chatted about it in a while. Excuse me. If I have e to the infinity, that's a really big number. So this is 1 over infinity. Do you remember what 1 over infinity is equal to? You say it's 0. And I don't know if you remember this discussion from limits or not, if your head was spinning from limits, but kind of on a side here. 1/2 is a pretty small fraction. Yeah. 1/10 is even smaller. 1 over 1,000 is smaller. 1 over 1,000,000 is even smaller. So 1 over infinity is so small, we consider it 0. So it's a teeny, 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 tiny fraction. So our answer to this problem is indeed 0. Good. And what else are we doing here? The limit as x approaches 0 from the right. We're going to talk about that in a second. Natural log of x over cosecant of x. Now, 0 from the right, we knew that the answer was positive or negative infinity for a lot of those problems. That's not the only time that you use that notation. The reason why it's appropriate here is if we're looking at natural log. This is my natural log curve. It passes through the point 1, 0. I have to say approaches 0 from the right on this side over here because there is no function on the left. It's not defined there. So we're only allowed to use the right-hand side. So the numerator is negative infinity because it's going down, down, down to negative infinity. Cosecant is related to sine. So it might be helpful to think of, I'm going to work on the side here, 1 over sine of x. So if I'm looking at 1 over the sine of 0, we know that the sine of 0 is 0. So this is 1 over 0. We treat that as infinity. So if 1 over infinity is 0, we treat 1 over 0 as infinity. So back in my limit problem, there's my infinity. So this is indeed indeterminate. So what we're allowed to do now is use L'Hopital. And L'Hopital says, find the derivative of the numerator and the denominator. So the derivative of natural log, if you recall, is 1 over x. Make sure you're using that golden ticket and that you're practicing all those problems, all those derivatives. The derivative of cosecant is negative cosecant cotangent. It's a long one. This is kind of messy. I don't want to put the zeros in yet. So I'm going to move the x to the bottom. I'm going to put the negative in the front. Cosecant is really the reciprocal of sine, so I'm going to put sine back in the top. Cotangent is really the reciprocal of tangent, so I'm going to put tangent in the top. I want this back to my most basic trig functions. And tangent is really sine over cosine. All right, we're looking something like that. So now we have to put that 0 in and see what we get. So 0 for sine is 0 twice. And 0 for x is 0 times cosine of 0 is 1. So this is 0. Still indeterminate. So what did we learn in the last problem? You can find the derivative again. So this becomes, in the numerator, I have it set up like a product rule, but remember that this is really negative sine of x quantity squared. So I'm going to do a chain rule just so I can save on space. The limit as x approaches 0 from the right, negative 2 sine of x to the first. The derivative of sine is cosine. The bottom is a product rule. There's no way to get around that one. So it's first derivative of the second plus the second derivative of the first. Okay. Hoping we can do a little bit of work here without having to do L'Hopital again. So let's put the 0 in and evaluate. Sine of 0 is 0, which is great news. Cosine of 0 is 1. So the top is a 0. Might be panicking a little bit. Oh no, I hope the bottom's not 0. So let's check it out. If I put it in here, this is 0 times 0, which is definitely 0. But cosine of 0 is good news. Cosine of 0 is 1. 0 over 1 is equal to 0. Awesome. So these are a little bit different, but I like L'Hopital's rule. The form 0 times infinity. Now, 0 times infinity, still indeterminate. I know that middle school part of you wants to say, well, anything times 0 is 0. Yeah, we lied a little bit when we told you that. Infinity times 0 is not 0 because they're both such strong forces. And this is not a very mathematical reason either. They're both strong forces. Who wins? Anything times 0 is 0. Anything times infinity is infinity. So it's not 0. But in order to use L'Hopital, it has to be a quotient. So I don't have a quotient right now. So 0 times infinity is still, we don't know. But you can manipulate this equation a little bit to turn it into a quotient. So I'm going to rewrite it. I'm going to say the limit as x approaches 0. You can move the x to the denominator. When you do that, remember your exponent rules. This becomes x to the negative 1. This is one of those things where every math that you've learned up until this point, you use in calculus. You use the fractions and decimals from middle school. You use all of the algebra rules. You use all of the algebra 2 rules. You use everything in pre-calc. You use a lot of geometry, not all of the geometry, but a lot. So my negative exponent from algebra 1. Natural log of 0, we talked about in that last problem, but just to remind you, looks like this. So 0 from the right, so this is going down to negative infinity. X to the negative 1 is really 1 over x. This is one of those function graphs that you should know as well. Looks like that. So if I approach 0 from the right, 0 from the right is headed up to positive infinity. Again, don't use that equal sign because it's not a real number, but it is indeterminate. So if it's indeterminate, we're allowed to use L'Hopital. So the derivative of natural log, we already talked about this morning, was 1 over x. The derivative of x to the negative 1 is negative x to the negative 2. Don't put the 0 in yet. You want to clean up your algebra. Otherwise, you'll still wind up with a big mess and zeros and infinities all over. So I'm going to take the x to the negative 2 and move it to the numerator. I'm going to take the 1 over the x, and the x actually goes in the denominator. So this is negative x squared over x. And those algebra rules, this becomes a negative x. You could have subtracted exponents. That would have worked as well. You could have called this x to the negative 1. Negative 1 minus the negative 2 is really 1. However you want to get there. If you put 0 in place of the x, your answer is 0. Awesome. For example 4, infinity minus infinity. Again, somewhere you want to say, oh, it's the same thing. Infinity minus infinity is 0. Not 0. One of those infinities is larger than the other one, but you don't know which one. So infinity minus infinity could be 0. It could be positive infinity. It could be negative infinity. We don't know. So we need to get it into that indeterminate form, but let's back up before we get there. 1 over sine of x is 1 over 0, which is infinity, minus 1 over 0 is infinity, so infinity minus infinity. Question mark, we don't know what that is. We need to be able to use L'Hopital, but L'Hopital only works for quotient. Right now I have 2 quotients. I want 1 quotient. Common denominators. So this is the limit as x approaches 0 of x minus sine of x all over x sine of x. And just double check. You want to make sure you are getting that 0 over 0 form. So the numerator is 0, the denominator is 0. We're good. Now we can use L'Hopital. The derivative of x is 1. The derivative of sine is cosine. In the bottom, I have an x sine of x. What kind of rule do we need? Product rule. So first, derivative of the second plus the second derivative of the first. So in the numerator, cosine of 0 is 1. So this is 1 minus 1. In the denominator, that's a 0. That's a 1. That's a 0. So this is 0 over 0. What do we have to do if we have 0 over 0 again? L'Hopital again. Let me switch colors here. All right, so the good news is when you find L'Hopital each time, when you keep taking the derivative, terms start to drop out because they turn to 0. So that's good news. The derivative of 1 is 0. That's gone. The derivative of negative cosine is going to be a positive sign. X cosine of x in the bottom is a product rule, unfortunately. So first, derivative of the second plus the second derivative of the first. That was all of this. And then at the end, the derivative of sine is cosine. Now, you can go through and combine like terms. There's a 2 cosine at the end, but I just want to be done with this problem. So I'm going to put the value of 0 in. So sine of 0 on the top is 0. This becomes 0 plus 1 plus 1. So this is 0 over 2. That's okay. 0 divided by 2 is 0. 0 is a perfectly acceptable answer. 0 over 0 is not, but plain old 0 by itself is. All right, I think I have 2 more examples for you. These can be a little bit tricky. I gotta take a quick break here and then I'll come back into example 5 with you. All right, and we're back, new location. Last two examples. If we're looking at 0 to the 0, 1 to the infinity, and infinity to the 0, again, all of these are forms where they're not a real number. For any one of them, you could almost make an argument that the answer is 0 or 1. There's conflicting information. So they are these other indeterminate forms. For example A, there are a few extra steps. If you go to look up examples like this online from another source, they might show you a little bit differently. But the way that it was shown to me was to put a y on the other side. And it's just going to act like a placeholder right now. By the way, if we put a 0 in place of this x, this would be 1 to the infinity, which again, we don't know what it is. So we put the y on the left-hand side. What that allows us to do is bring in a natural log. And with a limit, you can actually pull that to the front. So this is natural log of y equals the limit as x approaches 0, natural log of 1 plus x to the 1 over x. Now, the nice thing about the natural log piece is the exponent you're allowed to move around. So instead of 1 over x being on the outside, you can actually move it to the front. So this natural log of y is just going to sit there as we go through. So this is 1 over x, natural log of 1 plus x. So what I'm looking at now is this is a 1 over 0, so this is infinity. That second piece is natural log of 1. Natural log of 1 is actually 0, so this is infinity times 0. Again, we don't know what it is. Infinity times 0. The way it's written up there, if I read it like this, it's actually 0 over 0. And 0 over 0 is that indeterminate form that we can use for L'Hopital. So the left-hand side stays as it is. And this is L'Hopital, so there's my little notation that I use L'Hopital. So the derivative of natural log is 1 over whatever's inside times the derivative of what's inside, which in this case is 1 over 1. So if we simplify this a little bit, algebraically, this becomes 1 over 1 plus x. Now, pop that 0 in for x and we get a 1. But the answer is not 1. Remember, the left-hand side is that natural log of y. Well, we brought the natural log in so that we can move the exponent. Well, now we have to undo that. So don't forget to bring an e on both sides or rewrite this log into an exponential, whatever makes more sense to you. So y is equal to e to the first. But what's e to the first? It's just e. So y is equal to e. So you have that extra step of introducing the natural log. I believe that's the case on the next one as well. X to the x, this one's a little bit nicer. If you were to put that 0 in there, this looks like 0 to the 0. Again, not 0, not 1, not infinity. It's this crazy indeterminate form. So I'm going to introduce the y on the left-hand side. It just organizes it for me a little bit better. I have seen them online where they put the e and the natural log both on the right-hand side, but that's too much for my brain to handle at once. So natural log of y is equal to the limit as x approaches 0 from the right, of x to the x. This x that's the exponent I'm going to bring to the front. So this is x. Now I forgot the natural log piece, didn't I? On the right. Okay, so limit natural log of x to the x. There we go. So natural log of y. Actually, the natural log should have been up here. Now I can bring that x to the front. So this is the limit as x approaches 0 from the right, x natural log of x. If you put a 0 in for this x, this is now 0. Remember with natural log, it doesn't exist at 0. So we have to approach 0 from the right-hand side. This is going to negative infinity. So 0 and negative infinity, We don't know what they are, but I can't use L'Hopital yet. L'Hopital has to be for a quotient. So we had an example like this earlier on in this lesson where we brought that other piece to the denominator. So natural log of x over x to the negative 1. Now if I look at that 0 from the right, this is a negative infinity. That x to the negative 1 is 1 over x. So if I approach 0 from the right, this is infinity. This is indeed indeterminate. So we are able to use L'Hopital. So the natural log of y is the limit as x approaches 0 from the right. Remember, this is a L'Hopital problem now. The derivative of natural log of x is 1 over x. The derivative of x to the negative 1 is negative x to the negative 2. So natural log of y, the limit as x approaches 0 from the right. If you remember from the previous problem, this becomes an x squared over x. I'm writing out every single step here, that this is a negative x. Now, if I put 0 in place of that x, I do get 0. And you're like, all right, the answer is 0. The answer is not 0. Remember, we still have this natural log of y sitting on the left. You want just y by itself. Introduce that e on both sides. So y is equal to e to the 0, and e to the 0 is 1. Awesome. I like L'Hopital. These last two examples, they're a little heavy, but the other ones I really, really do like, and they are time savers. And you just want to be prepared when you get to the AP exam. They will also have some problems where it's just that function notation, where there's just an f of x or a g of x. And you ran into that a little bit with the product and quotient and chain rules. They want to know that you really understand the process and not just the algebraic terms that are in there. So work on the practice problems, reach out with questions, and we'll help you out. Thanks.